Oh, adesso dovrebbe registrarsi.
Sì, sì, sta registrando. Ora devi levare, penso, il video, Stefano, così poi vede solo me lui.
Ah, perfetto.
Sì, sì. Sì, sì, sì. Okay, ready to start. So the course that is supposed to be like of 6-7 lectures. So 2 like in December, today and tomorrow, and the other ones in January. The first 2 weeks after the holidays. So it's like about pluripotential theory on compact Keller manifold. So I prepared the first, I mean, I have the outline of what I would like to tell you, but of course I can change it depending on your questions or what you would like to see, or if you like to see some specific proof or whatever. So feel free to interrupt, to ask questions. I'm here for you, okay? So today I'm gonna start with the story, just like to motivate you why we would like to study such technical tools, and then maybe we can go a little bit in details and introducing some notions. So I'm not gonna use this, I'm gonna start from here, okay? So for all the lecture we are gonna work on a compact Keller manifold. So compact, so we have no boundary, Keller manifold. That is the data of a couple here. So X, that is a complex manifold of complex dimension n, and omega here is an extra structure endowed by the manifold that is called the Keller form of Keller metric. So it's just depending if you are in France, in Italy, or in the US. The Keller form, and what is this guy? So this guy is a 1-1 form with a lot of properties. So it's real, namely if I look at the conjugate of omega is equal to omega, so real in a very easy sense, that is closed, or more precisely declosed, namely d of omega is equal to 0, and in particular omega defines a cohomology class. Here the brackets here are for the cohomology in the H11 of X with real coefficient, because the form is real, and finally the form is strictly positive. So what all of this means? It means that if we look at the locally, in a coordinate chart, omega is going to be expressed in the following way. So we have I, so the square root of -1, the sum over alpha and beta of some coefficients that I call G alpha beta bar, dz alpha wedge dz beta bar. Okay, so here you see the structure of a 1-1 form. Here we have the holomorphic part and the anti-holomorphic part, and the coefficient here, the G alpha beta bar, are the entries of a matrix n times n matrix that is Hermitian in the sense of the Hermitian matrix, Hermitian and definitely positive. So saying that the form is 1-1 means that it decomposes in this way. Saying that the form is real means that the matrix here is Hermitian. Saying that is strictly positive means that the matrix is definitely positive. And the fact that it's closed turns out to be equivalent to have some nice conditions on the derivative of these coefficients. So these are functions, depending on the point of the manifold. Okay, so if it is the first time that you see that, maybe it's not very enlightening, so I'm going to give you a couple of examples that you can keep in mind with you for the rest of the time. But anyway, this is the structure, the very special structure that we have. Okay, So examples of Keller manifolds, compact. Okay, so I'm gonna put in the compact word. So the first example is CPN, the complex projective plane of complex dimension n, and this guy can be endowed by the so-called Fubini study metric. So this is a very special and famous metric. So this is Fs for Fubini study, and in this case, the coefficient of the matrix associated with the Fubini study, so GFS, are nothing else the second derivative. So let me write it down. So the second derivative with respect to first this is alpha, and then this is the beta bar of the log of 1 plus the norm of z to the power 2. Okay, this is how the coefficient looks like. I mean, this is something actually that I learned in Stefano's course a lot of years ago during the Keller manifold course, and then you can just make a lot of computation to see that this guy is gonna have all the nice properties here. Okay, I mean it's not difficult; it's just computations. Okay, so this is the first guy, the first example. The second one, I mean, I'm cheating a bit, but then it's going to be very useful for the following. We are going to take any submanifold, so smooth submanifold, or let's say CPN plus 1, so it's going to be an average surface, it's going to have complex dimension n, so this is defined as the zero set, the zero locus of an homogeneous polynomial, so f is an homogeneous polynomial of degree d. Okay, and then so if you take, so these are projective manifolds, and then in particular complex manifold, and then here the Keller form is going to be nothing else, you can guess it, is the restriction to V of the Fubini study metric. Okay, easy enough. And here remember this D here, because it's going to play a role in the following, okay? So these are the projective manifold defined by an homogeneous polynomial of degree D. You can take any positive D for the moment, okay? Nice. Okay, so now we have these special words, so Keller manifold. Keller manifolds, you can think of this as very complex manifold with a very special structure given by this Keller form. Okay, and then what we wanna do is to look at general problem. Look at the space of all Keller metrics on X. Matrix on X, and this space, I mean, you take any possible, I mean, the Keller metric a priori is not unique, you can take, there could be a lot of them, and you consider all this space. And this space, it turns out to be equivalent to the following one. So the space of all Keller metrics can be identified with the space, or the so-called space of Keller potentials. So these are just functions, C-infinity functions, real valued, such that when I look at omega, that is fixed, plus I d bar of phi, this is again a Keller metric. Is a Keller metric. Okay, so let me be more precise and add something. This can be identified as the space of Keller matrix.
Just one point.
Wait.
Can you see all the blackboard from the I see up to
I don't.
I do. Until
You do.
it's a calorimeter.
Okay, so maybe I should be here.
I think if you finish where you finish all, it's better. You see, the first line you have all.
Yeah, okay.
That's probably-
Yeah, okay, so here, for example. Something like this?
Yes.
Okay,
And on
thanks.
the other side,
It's okay. Yeah.
Okay, thanks.
Ma devi fare un vedi?
No, ne vedo solo un pezzetto. Vabbè, tanto questo qua. Ah, ok.
It's better like this?
Grazie. Ok.
Okay, so what I was saying that this can be identified with the space of calorimetrics in the same cohomology class of omega. This is why there is this omega that is fixed, okay? So we fix a reference form, and we look at all the other calorimetric in this cohomology class. So this is a cohomology class of forms, okay? As you know from differential geometry, you know. So why this space, I mean, the space of calorimetrics can be identified with the space of potentials. So for the space of calorimetrics, we expect to see a space of metrics, of forms. Here we have potential. Well, this is just a consequence, this is a consequence of the so-called DiNezza lemma that holds on the Keller setting. So again, maybe you're gonna see this on the Keller manifold course, but this lemma here just states that, let me write it down for you. So the lemma, the DiNezza lemma, states as following. So you take alpha, a smooth form that is D and the bar closed, the bar closed. So d of alpha equal to the bar of alpha equal to 0, then the lemma says that alpha is d exact if and only if alpha is d bar exact, I d bar exact, is I d bar exact. So now let's try at least to use this lemma to convince ourselves that the space of forms can be identified with the space of potentials of function. This is really like a central part of all the theory. So let's try to see that, to prove this in a sense. So thanks to the DiNezza lemma, we know that if we take any other omega tilde in the same cohomology class of omega, then we know that if we do omega tilde minus omega, this is d closed. So the d of both of them has to be to be 0, and also d exact, right? Because the cohomology class of the difference has to be 0. The cohomology, since the cohomology class of omega tilde is equal to the cohomology class of omega. This is just by our assumption here. So therefore, the DiNezza lemma says that, tell me if you can see here, says that omega tilde minus omega has to be I d bar exact. So this is equal to I the bar of something, but if you look at the degrees, so this is a 1-1 form, and here you're going to have the d bar of something, and the result has to be a 1-1 form. So the something is a function. So the d bar of a function. And I call this function phi. So this is nothing else in red. I d bar of phi. Okay, and this is actually this gives just the identification with the space of Keller matrix in the cohomology class of omega, and the space of Keller potential, real valued potentials.
Up to constant.
Up to constants. Why up to constants? Because here, when you add or subtract the constant, the d bar doesn't see it, right? When you take the derivatives, the derivative of constants are 0. Is it okay? More or less? Okay, this is just to tell you that the space that we are gonna study is this space, the H omega, the space of potentials, but actually thanks to something that holds in Kähler geometry, is very classical, this is equivalent to the space of Kähler matrix. Okay, so now we have this space, the space of Kähler potentials, and the question is, can we find a special metric inside it? Can we find something more particular? So question. So question, problem. Can we find a special metric? A special Kähler metric, Kähler potential, let's say. In H of omega. So this is the question. And maybe also for the following, I'm gonna always denote this guy here. Let me do that. Because I wanna keep it. Less space, so I can do that. So this guy here, I'm gonna denote it by omega phi. Okay? So this is the Kähler metric. Omega.
Excuse me? I'm sorry, I think there might be a problem with the sound. I'm not sure if you can hear me, but I think there may be a problem with the sound on Teams.
Yes, I can hear too.
Eleonora, I think there might be a problem with the sound.
Simone?
Ecco, sì, ora riesco a sentire, prima non si sentiva più.
Simone?
Mi sente? Mi sente?
Se no sul computer, mi sa che-
Sto usando l'audio.
No, leva il cavetto. Non so se è collegato.
Ah, devo levarlo? Simone?
Mi sente? Pronto? Pronto?
Gli scrivo?
Si sente?
Ho levato tutto.
Yeah, I can hear now. And for a second, there was a problem with the sound,
No.
but I think I can hear now.
Simone?
Mi sente? Pronto? Pronto?
No. Simone, se mi senti puoi parlare.
Sì, io la sento.
Ah, ok.
Ok, è
Vai.
che adesso prima non si sentiva più l'audio.
Ah,
Quindi, ok, dove?
Ce la potremmo fare. Vai.
E no, perché prima non si sentiva l'audio, quindi io volevo...
Ah, volevi solo dire questo?
Sì, sì, sì.
Va bene, ok.
Vai, no, mi scusi.
Adesso si sente?
Adesso sì, adesso sì.
Ok, thanks. Andrew, do you have a question?
No. It was just
For the
there was a
audio?
problem with the sound for a second.
Ah, yes.
That was.
Okay. So now you can hear me.
Yes, that's fine.
Okay, so I'm gonna try just to use the internal microphone. Okay, so what I was saying is that I was giving the expression of this Ricci curvature. So this is gonna be just the second derivative of the log of the determinant of the Keller form associated to omega phi, to the emission metric associated to omega phi. So this is gonna be G phi alpha beta bar. Okay, so maybe, I mean, it's not very complicated. This is an emission matrix. You take n times n, you take the determinant, this is a function, and you take the log of this function, and then you compute the second derivative, so the holomorphic anti-holomorphic one. Okay? And again, you can be assured that in the non-Keller setting, this is way more complicated. So this is very something on the Keller structure. Okay. But anyway, so something I would like to highlight, to underline, is that this equation here is an equation, yeah, I'm missing something, is an equation of forms. So this is times, this is what I was missing, times d zeta alpha wedge d zeta beta bar. Okay, so this is what I wanted to write it. So here you have a 1-1 form equal to some coefficient, a 1-1 form. So this is an equation for differential forms. It means a system of equations. So it could be very complicated. And now the question is, so let me call it KE. Where is my red? I should keep it for the rest of the year, at least. So KE, and the question is, can I solve KE? Yes, no, or when? The answer is yes and no, because the equation, the Cayley-Einstein equation, have a very somehow easy topological abstractions. And now I'm going to show you this abstraction. The abstraction comes out easily when we look at the cohomology classes. So at the level of the cohomology classes, the Cayley-Einstein equation rewrites in this way. I take just the cohomology class of both sides, omega phi, and then lambda times the cohomology class of omega phi. So this now is an identity given by the Cayley-Einstein equation. Now we use the second magic of the Keller word that says that the cohomology class of the Ricci of the Keller form does not depend on the form. So here I can put whatever form I like, and Keller form, and in particular I put the fixed one, the omega, the one we start with. So second magic, and the third magic, it turns out that this cohomology class actually is a topological invariant and is equal to the first rank class of the manifold. That this is nothing else that also the first chain class of the anti-canonical line bundle, so I'm using additive notation, that is equal to minus the first chain class of the canonical line bundle. Okay, and so this is actually very strong because it's going to give you the relation, a strong relation between the topology of the manifold and the metric structure by the ratio of a form. Okay, anyhow, so now let's look at this equation here. So here we found that the Keller-Anton equation implies that C1 of x has to be equal to lambda omega phi, that is also equal to lambda, the cohomology class of omega, right? Because omega phi was in the same cohomology class. So maybe let's look at this. Okay, and this lambda here, this lambda was a real number, and this cohomology class was somehow positive, because we said that omega was positive. So what this means, it means that, look at this, we have C1 equal to lambda times something positive. So it means that C1 has to have the same sign of lambda, right? Because you have C1 equal lambda times something positive. So this tells us that C1 has definite sign. So we have three cases. We have the case C1 negative, that is equivalent to the case when lambda is negative. That we have the case C1 equal to 0, that is equivalent to the case of lambda equal to 0. And then we have the case of C1 positive, that is the same of lambda positive. These are the three cases. And what one can see after is also very, I mean, maybe first some definition. When a manifold satisfies C1 negative, we say that the X is called of general type. So this is just a name. General type. In the case C1 equal to 0, X is Calabi-Yau. Calabi-Yau. And the case C1 positive, X is called Fano. So these are just names, but you should know that not all the Keller manifolds satisfies one of these three positive, these properties. So this is why this is abstractions. The Keller-Einstein equation tells me that if we want to hope to solve, we have to study, to treat one of these three cases. So let me just make a remark. So this is just an observation. You can keep it for you and then do the exercise when the time will be. So just I'm going to give you a very, very easy example of something that does not have the property of C1 of definite sign. So examples. If I take this, yes, the sphere S2, so CP1, CP1 of the sphere, the Riemann sphere, times an elliptic curve of genus 2, for example. So the surface with two holes, then this does not have C1 of definite sign, okay? And you can construct in this ways many other examples. You can take CP1 times a surface with a lot of holes, okay? So you're not going to have this property. This is why I'm saying that this is a real obstructions. Okay, so now we are gonna assume. So assume we are in one of these three cases. So C1 negative, so X of general type, X Calabi-Yau, or X Fano. So we are in these three cases, one of these three cases, and the question is again: can we solve Keller-Einstein? Can we solve the equation? Once again, the answer is yes and no. So what it's very important to say at this point is that the Calorimeters equation is equivalent to solve a complex Monge-Ampère equation. So here it is, our Monge-Ampère guy coming into the picture for the first time. A complex Monge-Ampère equation that is going to write in the following way. So omega plus I d bar of phi to the power n. So remember, maybe I would say omega phi is Ke, is scalar constant, if and only if omega phi solves the following Calorimeters equation. So omega plus I d bar of phi to the power n equal to exponential of minus lambda phi plus a smooth function h times omega n. Where here this h is a smooth function that depends on omega, is a smooth function on x, its real value. And of course, when you look at the, let me denote this exponential of h in the following one, I'm going to denote this with f. Okay, so f is smooth and strictly positive in this setting. Just like to make my life easier. And then this is, I'm going to denote with MA for Monge-Ampère, and then here I'm going to put a lambda. The lambda is here, right? In blue. Is the coefficient in front of the phi. Okay? So why, so first of all, why I say this is a complex Monge-Ampère equation, this is a non-linear PDE. So first of all, this is the solution, the function we are looking for, the function, the unknown function. This is the unknown, this is the reference form, so it's fixed, we know it. This is the unknown, and this is known. This is something that is a data of the problem, okay? Okay, so we have to look for phi. And why I say that this is non-linear, let me write it down in local coordinates, what it means. In local coordinates, this equation is equivalent to the following one. You take the determinant of the emission metric given by the form of G alpha beta bar of the fixed reference metric plus the second derivative of d zeta alpha, d zeta beta bar of phi. So this is the second derivative of phi. And then I ask that this determinant is equal to exponential of minus lambda phi times f times the determinant of the G alpha beta bar, where G alpha beta bar was the matrix associated to omega. So this is just, so here in a sense, I'm saying that I take a form, I do the wedge product n times, and this is actually equivalent to taking the determinant of the emission for the emission matrix associated. This is multilinear algebra. Okay? So maybe this is why now from this expression, the fact that here you ask the determinant to be something fixed, you see the non-linearity of the equation, right? Because the determinant is highly non-linear. Okay. So this is
no. Why actually is known?
Yeah, H here is just the ratio of omega is equal to, has to be in the same cohomology class of lambda omega. So this is equal to lambda omega plus IDD bar of a function, and this is H. So this is why it's known, because this is fixed. I mean, this is also from here. My question, I don't know if you want to see the proof of this equality, this equivalence. I don't know. This is also up to you. You can ask me even later, okay? By the way, I plan to make like a pause in between the two slots, but maybe I'm gonna finish with the story, okay? And then we make a small break, just to breathe. Okay. Yes. So this is like we see the non-linearity of the equation. Non-linear. The equation MA of lambda is non-linear. Warning. Okay. So a priori we are not able to solve this. And then now I would like just to conclude the story. So what's the story? Let's summarize. So we say that we wanna look for special metrics, special guys. Special today means scalar instant, so metrics that solve this equation, whatever it means. Then we say that this equation is equivalent to a PD, a nonlinear PD, that I write like this. So the unknown, the function I would like to look for is this phi. And now the question is, can I solve the motion pair equation? And the answer is again, yes and no, depending on the sign of lambda. So here is the end of the story for the moment. So we have the case lambda in the lambda negative or 0. We have a result from Uben Yao in the lambda strictly negative case, and then the result of Yao in the lambda equal to 0 case at the end of the 70s, saying that if, let's say, that there exists a unique solution phi, smooth function, a real coefficient of MA of lambda, where the uniqueness here is up to a constant when I look at the case lambda equal to 0. And also when I look at the case lambda equal to 0, I also have to assume, so let me put it here. So if lambda is equal to 0, I also have to assume that the integral over x of omega n, so this is the volume, has to be equal to the integral over x of f omega n. So I mean, this is a compatibility assumption, because let me do like here a remark, because this is it's going to be very, very important. Let's take the case lambda equal to 0. The motion pair equation turns out to be omega plus IDD bar of phi to the power n equal to f omega n, right? This is our equation. And now, of course, if we wanna hope to solve this equation, clearly we have to have the inequality when I take the integral at both sides. But this guy here is equal to, now you have to believe me, or we can do the exercise later. This is thanks to Stokes, is nothing else than omega plus omega to the power n. So this is Stokes. We can do the exercise together if you want. So you see that a compatibility assumption is that the volume of the manifold has to be equal to this f omega n. Okay? So this is something really unique to require. And again, why in the case lambda equal to 0 we need to normalize, so to choose to have uniqueness, so we have to choose, like we have to normalize in some way, because otherwise I would have phi, and phi plus a constant would be again a solution, because the second derivatives are gonna kill the constant again. Okay, and just to end the story, now I don't have maybe there. To end the story, and I'm going to make a small break. The case lambda positive is missing. I mean, it's missing in my story, it's not missing in the literature, but it turns out that the lambda positive case is much, much, much more complicated, because it's not always possible to solve. I mean, this is the difference from the lambda negative or zero case. So in the lambda positive case, so more difficult, it was proved, I mean, I would say recently, 6 years ago, in 2014, by Donaldson, Chen, Donaldson, Son. Let's put in alphabetical order. That
And can, otherwise he gets.
yes, let's say independently by Diana. The same year, it was like this was the outcome of a long fight between mathematicians. So there exists a solution phi of MA of lambda. So equivalent, it exists a Keller-Einstein metric on a Fano manifold. So this is a Fano case. It was just a name. If and only if the manifold X is K stable. Okay, so I'm not going to talk about this notion. The only thing I would like to say, and this is an algebrogeometric property of the manifold. So this theorem makes a link, I mean a very deep link between the metric structure, the analytic structure of the manifold, the fact that there exists a Keller-Einstein metric, with the algebrogeometric properties of the manifold. And if you are interested in that, you can go and see Giulio Codogni. He's an expert on the right part of the story. Okay, so outcome, lambda negative or zero, we can always solve, and we are happy. We have some compatibility conditions, but we are very, very happy. Lambda positive, we cannot always solve, but we can solve if the manifold have nice properties. And maybe just to conclude, actually this result was like a big breakthrough, also because like solves in a special case of a Fano manifold another long-standing conjecture in Keller geometry. Okay, so this is like a part of the story. There is much more to go and to do. Okay, let's take a couple of minutes break, and then we start again. Okay.
Very good.
Very good. Yes, we start. I don't know, like 5 minutes.
Okay,
Mostly.
even 10, I don't know.
Yeah. Yeah, also because we are, yeah, then we have half an hour.
Chiaro tutto chiaro?
Sì, io ho una domanda, due domande. Una stupida.
Ah, sì, let's try with the question. Vai.
Can one say for which Keller manifold you have if you have a Keller manifold, can you say for which classes you have? So suppose you have a manifold and you know there is a Keller form. Can you say for which classes you have other Keller forms?
Okay, so here, so you remember that when you look at the, you mean the Keller-Einstein?
No, Keller in general, it's independent of it. I mean, I'm quite ignorant of Keller.
Okay, no, say it again. So, okay, right.
So the first question is it always true that you have a Keller form on a compact manifold? Or no?
No,
Okay.
this is not. For example, oddio, come si chiama? The off surfaces. So you have some.
modulo.
No, but I imagine that also. No, okay, that makes sense.
Yeah, so
But
you have a lot of complex manifold that are not Keller, because already to be Keller, you have to be, the odd numbers have to be special. For example, the even ones have to be odd or something like that. So you have like also topological abstractions to be a Keller.
Suppose you have a Keller form.
Okay.
Can you
So
say
you are
the set of Keller of homology classes for which a Keller form exists?
It's an open set when you go into cohomology.
Okay.
Because it's an open condition.
So because you fix here the homology class of the Keller form.
Yes.
But there might be Keller forms of other homology.
Yeah,
So
sure.
Can one say something on the set of homology classes?
This is called the Keller cone, and it's open.
It's cool because if you have a Keller class, then lambda times omega is still Keller.
So you can take all the lines.
And there are cases in which all classes have a Keller form?
No, because minus omega is not there.
No, okay.
no, and then also like, so this is a cone. So here, this is in the interior here. In the interior, you have the Keller cone, if you want. Keller cone. So, okay, this is 0. This, you are not taking the boundary. So already, if you take the closure of the Keller cone, there are cohomology classes that are not Keller, the ones you are in the boundary, for example.
And there are classes in which is the widest possible.
There are something that we are gonna consider. I mean, not all. So, for example, we are, yeah, maybe. I don't know if the
For
widest
example,
possible.
if you make a blow up of some surface and take a Keller thing downstairs and you blow up, then you get a form which is semi-positive. And therefore it's on the boundary of the Keller cone, but it's not in the Keller cone upstairs.
Yeah, but it was
no, I'm
asking
saying
something
there are
else.
examples in which this cone is as wide as possible.
The Keller cone, you
yes,
mean?
the Keller cone.
What does it mean?
Well, it's not.
Remain sharp. You mean that it remains sharp?
It's not clear, at least to me, what you mean by the largest possible.
So, for example, I don't know, examples of Keller classes. If you take, I don't know, for example, just to give you an idea what this would be. If you take the product of CP1 and CP1, and you take A omega Fubini studi plus B omega Fubini studi. So for A greater or equal than 0 and B strictly positive, for example, this is always, there are all, so you take R plus times R star plus. So it's quite big. But then, I mean, because maybe there is maybe no notion of this maximality, there is no good definition of this maximality thing. But this is a good point here. So here, this is the Keller cone, so all the cohomology classes. We are gonna also, like maybe today or later on, looking at other cones of cohomology classes. So what is called the pseudo-effective cone, the net cone, the big cone, and they intersect somehow sometimes. Okay? And then you have to look another one.
No.
That's it.
So you have the core of color form. And for each
This is the
Keller
cone of
classes.
Keller
Every
classes.
possible.
Of Keller classes.
of every possible color classes.
Keller classes.
Yes, exactly. The set of Keller classes is a cone, open cone, in H11.
So in here, in a point in here,
It's a class omega. And for each class you got H omega. And for
each class,
you got H omega, the
yeah, sure, yes, and they are all different. Okay, so you take, here you have H omega, omega 1, let's say, okay? And let's say that you want to be here, omega 2. Then you have H of omega 2, okay? And if these classes are not the same, then these spaces a priori don't talk to each other, okay? They are very different space. I mean, we're not going to talk about this in the course, but these spaces, these are infinite dimensional Riemannian manifold. And there is also like the study of all the geometry and the metric that you can put on this space. But this is another story again. Okay?
so there are some people study the geometry of H omega.
Yeah, me, for example.
You can give another talk about that.
Yeah. Yes. Okay. Okay.
Maybe there is a very stupid question, but
Yeah,
is there
sure.
any kind of color compactifications that
Or what?
a non-color manifold?
Or non?
Non-color, non-compact manifold, and you put in, can you put it in some compact?
Keller non-compact.
Yes. And then you put some compact. To go back to setting the compact color manifold we are talking
Yeah,
about.
but then, I mean, here you start with compact because there are a lot of things that doesn't work if you don't take compact. And
I try to go back to compact form by compact.
yeah, but a priori, well, I mean, the pluripotential theory in the non-compact case has not been developed.
Okay.
at the moment. And the point is that if you have something non-compact, maybe you would like to have an asymptotic behavior. You would like to prescribe the asymptotic behavior at the band, at the infinity, if you want. But this is a completely different story. So this is not what we want. So one of the reasons why we want compact, I mean, is already hidden here. So in these theorems here, you use a lot the compactness of the manifold, so a lot in a significant way, and it's gonna be clear like in a minute. I'm gonna be more precise. Okay. So the compactness is hidden in here for the moment. Okay. So I think I can start again, maybe slowly. You're tired?
Okay.
Yes, maybe. No.
Okay.
Well, and actually, so what I would like to
So we have talk until 4 p.m. 4:30. Past 4.
4.
4.
Otherwise, I'm gonna kill you. I don't want to. No. No, but like I think
Okay.
that like I'm gonna take some time just to motivate you for what we're gonna do like in the following. So this was a lot by just this story. So really just the story of the smooth case. So why I say the story of the smooth case? Because now everything, we start with a manifold that was smooth. We start with a reference form that was smooth and strictly positive here. And we were looking for a function, we were looking for a smooth solution. So smooth, 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 regular, regular, regular. And what I would like to do in the course is to look at the singular case. So singular can mean a lot of things, and then I would like to say what do I mean? I do mean by singular, and why we want to look at these singular cases. So it's just gonna be the rest for today. But again, so I told you a story. If there is something you would like to see more details, that you don't understand, that you would like me to prove it, just ask me, okay? And then we can go back even at the end of the course, and then I can remodulate everything. Okay, let me erase everything. Maybe not here. Here. And yeah, come on, I'm gonna erase everything. Voila. So just remember, maybe here, summary, the thing to remember, Keller-Einstein equivalent to omega phi is Keller-Einstein. If and only if omega phi to the power n is equal to exponential of lambda phi times f omega n, okay? So this is what you should keep in mind. And x smooth. Or complex dimensional. Okay. And now the question is, what about the singular case? So singular, as I said, can mean a lot of things. I'm gonna describe for you. So singular, it can mean that there are 3 cases. The reference form, the reference form before was Keller, was omega, is not Keller anymore. Is not a Keller metric anymore. Singular could mean that the manifold, the underlying manifold, that was X before, is not smooth anymore. Meaning that it could be a singular, it could be could have some singular point, for example, this. Can you see? No? The singular point is here. And the third case is that the metric omega phi is not smooth anymore, not smooth. Or better, that phi is not a smooth function anymore. So 3 cases. The manifold can be singular, the reference form cannot be Keller, or the outcome, the metric we find is not smooth anymore.
But
So the potential is not. Yes.
no, Keller means indefinite or maybe
This one?
not closed or
Indefinite. I'm
Indefinite.
gonna say better. Yes. So maybe here not Keller anymore, but the reference form could be just given by the reference form is given by
Smooth 1, 1.
theta, that is just a closed real 1, 1 form. So you have all the properties except for the sign. So all the others are okay. So in particular, this defines the cohomology class. In the H11. Okay, so now you see 3 cases, but actually these 3 cases are very much related to each other. And this is what I'm gonna, so let's say this is the first setting, 1, 2, 3. This is 1, this is 2, and this is 3. Okay. So let me tell you how, to start with, how 1 and 2 are related, the first 2 settings. So these are related because if we look at, I don't know, a singular manifold, let me call it Y, so this is singular, okay? Singular, you can think something as the picture, or something with some point like cones or cups, something like this. So this is singular or complex dimension n, and this is a Keller variety. So this is how it's called. So Y is a Keller variety. So I mean, this is just again a story to motivate you. You don't need to know all these notions. This is a Keller variety. So variety just a manifold with singularities. So it's a regular somewhere, and then there is a notion of being Keller, okay, for this variety. Okay, so we have this variety, and actually something that algebraic geometry tells us is that we can always resolve the singularities. So we can take pi, that is a resolution of singularities. I mean, you don't need to know what this is, but you should just know that this is a bimeromorphic map. So this is a map that goes to Y, to X, and the pullback of course, you have the pullback of the form, omega Y. This here, this X, is again a complex manifold of dimension n, and this again actually now a Keller manifold. Why manifold? Because now I resolved the singularities, I performed some magic, I resolved the singularities, I end up with something that is smooth.
Well, but the Keller form is not pi after star It's something
No,
else.
the Keller form is something else. Keller
Ah.
manifold with Keller form omega x, okay? With the Keller form, yes, maybe with the Keller form. Thanks for the
Omega
session.
theta,
Keller form omega, no, just because just omega x. So, and then the point, the important point to make is that if you look at this guy here, so here we started with the reference form. Here the reference form is the pullback of the one we started with, and now we call it theta. So if we look at this theta now is the pullback of a one form, so it's again 1, 1. It's the pullback of a closed form, so it's again closed for the definition of pullback. But the point is that this form is just semi-positive. Why semi-positive? Because it's gonna be 0. So you can think of the resolution of singularities like this. Here there is the singular point. You have two different directions that are singular, and on this singular point you're gonna put an exceptional divisor, a CP1. So let's say in dimension 2, n equal to 2. Okay? So here you have these two different directions, and you don't have your good. So here you have these two tangent directions that are gonna be this. This is why the manifold X is not singular anymore, but it's smooth. But look at this. When you look at the push forward of this line, this complex line, this is a point, right? So this theta is gonna be 0 on these directions, because when I go the push forward of this direction is just a point. Okay. So this is why it's 0. It's just semi-positive. Okay, and you see, if we have, so theta is semi-positive, closed, and real. So theta has a lot of nice properties, but it's not Keller. Theta, so the outcome is that theta is not Keller. Okay? And actually what it turns out, it can be proved that maybe here, the Keller-Einstein equation on omega y, on y omega y is equivalent to a complex Motion-Pair equation, a Motion-Pair equation on the smooth guy, on x, that writes as the following. So let me write it down. I to the power of phi to the power n, exponential of minus lambda phi, f omega n. So what's the difference with before? Look, so now again, x is smooth right now, but what's the difference between this equation and the classical one? So let me write it here. So this was omega plus I dv bar of phi to the power n. So what's the difference? Well, the difference is that the reference form is not anymore Keller, not necessarily Keller, and that this function that was strictly positive, you remember, was the exponential of something, in this case can be 0 somewhere. It can explode. So f can go to plus infinity. In the other case, was a smooth function on the compact manifold, so in particular bounded. Okay.
Omega is theta.
Sorry. Let me say volume form. Okay. No, here you take the volume form because so you could put. I don't put theta n because if you want all the degeneracy is inside this f. This is why I say that f can be 0 or explode. So this is why here you can put a nice volume form, whatever you want, Lebesgue, for example, dv, okay? dv is for a generic volume form, very, very nice. Okay, so, and this here, it's called a singular motion pair equation. Singular singular motion perturbation. So again, what does all this story with a lot of math behind tell us is that if we wanna try to push further the theory and look for Keller-Einstein on singular manifold, we have to study singular motion perturbations of this type. Okay, and this is actually what we're gonna do. So this is why we want to look at this singular stuff. Okay, and then maybe just to conclude, so here I made the link in between 1 and 2. Let me also tell you something. So this was the link in between the first context and the second context. Let me also make the link with the third one. So what it means that metric is not smooth. Well, here, if you want already to make like the simplest link, when we look at this equation, the expectation, let's say, let me erase here. So this was singular motion pair. And here is the warning. The expectation is that even if we can solve, phi is not going to be smooth a priori in general. Maybe smooth only on a Zariski dense set. But not on all of X. And this means that the resulting metric, theta plus I to the power phi, is a singular metric, because the potential is singular. But we are really going to see all of this in details. Okay. So in this special situation, phi is not smooth. And the one question that we are going to ask ourselves also in the following is, so here we have the link 1 and 2. Let me also make the link with 3. With 3 is that when we look at the singular motion pair equation, so look at the singular motion pair equation, singular MA over there. So theta plus I to the power of phi to the power n f dv. So I said that I'm going to show you that phi a priori is not a smooth function. And one could ask, a priori, it could go at minus infinity somewhere. And a priori, one could ask, okay, can we understand better? Can we prescribe how fast it goes to minus infinity, for example? So question is, can we prescribe the singularities, okay? Can we understand? The singularities of phi. This is the question, and the answer is yes and no again. I mean, this is a long story and a very difficult problem, but what we did with my collaborators, Chinlu and Tamas Darbase, also what I'm going to show you is that, let's say, yes, if we prescribe the behavior at the beginning. So what do I mean by this at the beginning? So what do I mean by this? I mean that I'm gonna fix. So what I'm gonna do is that I'm gonna fix a potential phi, a function with a precise asymptotic behavior, with a precise behavior, but this is something that I fix, okay? Precise behavior, I'm gonna go here just to be sure that you're gonna see, and what I'm gonna solve and I'm going to solve the motion pair equation, the singular one, asking another condition, asking that when I look at my solution and the fixed one, the difference is bounded. So this is going to prescribe, this is going to give us a better understanding of the solution, because we solve asking that the solution goes as the same singularities of phi. So here is phi as the same singularities of phi.
Then you want all the other inequalities.
3. This is absolute
not
value.
not only small or equal. And the norm, yeah.
The norm, yeah. Yeah, so it means that phi is in between capital Phi plus a constant and capital Phi minus a constant. So both sides. Okay, and this is what we call the singular motion pair equation with prescribed singularities. So here, singular motion pair with prescribed. So this is what we are gonna go do in details in the course. So we are gonna look at singular motion pair equations with non-precise asymptotic behavior and singular motion pair equations with a precise asymptotic behaviors. And like in the next lectures, I'm gonna start with like all the notions and like some details to understand better the difference between these two equations. They are of complete different natures somehow. Okay, I think it's a good time to stop.
Okay.
And see you tomorrow. See you tomorrow. Yes. Bye. Bye. Yes, I've done 1/3 of what. Okay, bye.
Ottimo, solido. As usual.
Yes.
Beh, vabbè, poi a un certo punto 3 parole sul fatto, il motivo per cui uno studia le cose singolari, perché c'è la geometria algebrica.
Lo devo dire pure quello?
Beh.
I can tell you now if you want.
You can tell me.
So
yes.
this is the question, Stefan's question, so it's a question for you. So why we want to study, I mean, this is the analytic side, right? I said, we want to study singular PDEs, in a sense, singular nonlinear PDEs, two type of them, and what's the geometric outcome? Geometrical outcome is like this singular Kähler-Einstein symmetric on singular manifold, and all the geometric motivation, the big one, comes from we are trying to classify Kähler manifolds. So we said we are gonna we have boxes and we put all the manifold, all the manifold with Kähler-Einstein symmetric in the same box. So we are really trying to classify things, and we are trying to, I mean, in a sense, we are trying to see if there is an analytic way to prove the minimal model program. So the minimal model program is something in birational geometry, saying that you start, if you want me to write it down, I can write it down, but the minimal model program is say you start with a projective manifold, so a projective one, you say, okay, I'm up to B rational maps, I want to find the best candidate. So I can blow up and blow down. The best candidate, yeah. The best candidate. And the best candidate means when the canonical bundle is NEF, whatever this means. You asked me, I did not define yet.
This will be said later.
Yes, this could be said later, but there is this best candidate. And so this minimal model program is known for the moment up to dimension 3. So there is a lot going on, and higher dimension we don't know if we can we can find it. But let's say that the existence of this special metric could help in this reaction. So to classify projective, I mean, we start with projective manifold. So if we can do with analytic methods, we can classify even Keller manifold. That could be even better, right?
Because the point is that this best candidates are usually singular.
Yes.
Even when
yes,
the
this I didn't
original
say.
manifold
Yes.
is smooth.
The best candidates are usually singular. This is not true in dimension 2.
No.
In dimension 2 was the Italian school at Castelnuovo that proved it, that we can always find, and the best candidate was always smooth. In dimension 3, this was Mori, that gained the fixed method for this, to prove that the minimal model program is okay in dimension 3, but the best candidate a priori is singular, most of the times.
So this is one of the reasons why
we want to study
singular.
singular. Yes.
Singular guys.
This is a lot, because this is really like. But there is, I mean, the motivations come from geometry, and then this is all went on. But actually, like, one of the motivations to study motion pair is also related to optimization theory, to dynamical system. There are all this theory of currents that is going to come into the picture very soon. So there are a lot of fields interplaying.
That was the question again. So
Yeah.
motion pair appears also in optimal transport, right?
The real one.
Yeah. So does it give any interpretation of phi in terms of some?
No, because the real okay, the real motion pair and the complex one, a priori, they are very of different measures. Also, the regularity results for these two operators are different, but they talk together well in the case of toric manifolds. I mean, toric manifolds, for example, CPN, there are a lot of symmetries, and in the case of toric. In the case of toric manifold, the complex motion pair. In the case of toric, you have a toric manifold. You can always associate something identified by delta, that is a polytope in Rn. So let's say this was a complex dimension n. There is a way of going from one side to the other, because you have a lot of. I mean, here you have, let's say, a torus of symmetries on X. Anyway. So you have this polytope in here, and the complex motion pair equation, the complex one, is gonna become a real motion pair equation on the polytope. But then I don't think that. I mean, in here there is not really a optimization problem, in the sense that you don't have a cost function or something. You could think that in that way. There are some paper of Robert Bergman in this reaction, but I'm not really. I mean, it's not something direct. It's really you have to change perspective. But in some cases, so in the toric case, you can always do that, because otherwise they don't talk to each other. So there is no way. I mean, this is really sorry. This is really everywhere. Okay? Anyway, thanks. And even after the lecture, feel free to contact me if you want to tell me to slow down, to be faster, to, I don't know, to prove something, whatever. Okay, thanks a lot, guys, to be also on Zoom.
Great. Eleonora, could I just ask what time the lecture will be tomorrow? In the announcement that I got, it was uncertain.
Ah, no, it's the same, 2:30.
Okay, excellent.
It's the same of today,
The
2:30.
link, I will
And
send
the
it
link,
today.
and the link is gonna be on my webpage. There is now a section teaching, and because the link is gonna be different day by day, and then I'm gonna put it today. So Stefan is gonna create it right now, and then I'm gonna put it.
Excellent, fantastic. All right, see you tomorrow then.
Guys. Ciao.
Tomorrow's, for people who follows in person, tomorrow's class will be in Aula Grassano di Fisica. Same time, not yes.
Not here?
Not here.
What is it? Further, this corridor?
For this direction, yes.
Allora, DiNezza, tanto
Sì.
adesso viene Carla.
Allora, aspetta, lo faccio subito.
Metti anche
Posso
le
chiudere?
registrazioni.
Io chiudo, Ciao.
Sì.
Metti
Ma
le
tu
registrazioni
devi...
sul sito.
Vabbè, io chiudo. Tu devi finire la
Io
registrazione.
devo chiudere la registrazione, va bene?
Ma si legge? Sì, si legge, no?
Sì, abbastanza. Sì. Dunque,
Non so se si può mettere a fuoco la telecamera.